So with our last video, we got into some very basic chemistry and we started to talk about atomic structure, and we left off talking about the electrons and the fact that they're kind of moving around the nucleus in these structures which are known as orbital shells. What I want to do with this particular video is talk a little bit about where these electrons are in orbital shells, and kind of give you some rules for assigning them to certain orbital shells. Again, the reason being because where electrons are located around an atom's nucleus is going to give you all sorts of information that you need to know for anatomy and physiology to understand how these atoms are actually going to interact with each other. So in the previous video, we talked about the fact that the number of protons and number of electrons in a particular atom is going to be equal. So here's my Bohr model of hydrogen. It's got a single proton, which means it has a single electron. And what we see with these electrons is they're going to fill orbital shells that are closest to the nucleus first. And you see that happening here with hydrogen. Over here, I've drawn a Bohr model of helium. So helium has an atomic number of 2. It's got 2 protons, which means it also has 2 electrons. And those 2 electrons, again, are going to fill the shell that's closest to the nucleus first. But that particular shell can only hold 2 electrons, and then it's full. It can't hold anything else. So if you look at this Bohr model over here of lithium, it has an atomic number of 3. So 3 protons in the nucleus. We've got 3 electrons kind of moving around that nucleus in these orbital shells. You'll notice its first 2 electrons go in this first shell, and the next electron is going to go in the second shell because it can't fit. It can't fit into that first shell. So there's a rule that explains where electrons are going to go around the nucleus. It's called the octet rule, and this is something you're going to want to be familiar with because it's going to help you to know what's going on with atoms and how they're going to act. So the octet rule says basically this: the first shell, this is the one that's closest to the nucleus, can hold a total of 2 electrons. The second shell can hold 8 additional electrons. The third shell can hold another 8, and there are shells after that, and in chemistry this can get really complicated, but good news, in anatomy and physiology we're typically dealing with smaller atoms, and so these rules, if you know just these 3, can get you to where you need to be with anatomy and physiology. So with that being said, what I want you to do is go ahead and pause your video in just a moment, and I want you to see if you can draw Bohr models and properly assign electrons for a couple of different atoms. So first of all, carbon, which has an atomic number of 6, and then argon, which has an atomic number of 18. So go ahead and take a whirl at that, see if you can use this octet rule to be able to understand where these electrons are going in the orbital shells. So hopefully you paused the video and took a little bit of time to draw out a Bohr model for carbon and a Bohr model for argon. I've got these up here for you to see so that you can kind of check your work. We know that carbon has an atomic number of 6, so there's 6 protons in the nucleus. That means we're also going to have 6 electrons, right? So here's our first orbital shell, the one closest to the nucleus, and 2 of carbon's electrons are going to be there. But once those 2 electrons are there, it's full. There's no more room for electrons. We still have 4 electrons that are part of carbon that need to go somewhere. And so they're going to go in the second shell. So you can see we've got those 4 electrons there, 2 electrons here. So we've got equal numbers of protons and equal numbers of electrons. And this is what carbon looks like. Over here is argon, so this one just a little bit different, 18 protons, and when there's that many protons, I start getting lazy and I start using just 18 plus as my kind of shorthand way of representing that. But because we've got 18 protons, that means we also need to have 18 electrons. The first shell has 2, but we still have 16 more that need to fit around the nucleus. The next shell has 8. So in the first shell and the second shell, we have a total of 10, but there's still 8 electrons that need to fit around the nucleus of the shell. So if you look at this outermost shell of argon, that's where the last 8 electrons are, okay? So this shell is full, this shell is full, this shell is full as well. I want you to compare carbon and argon to each other for just a minute. Argon has an outermost shell that's full. Carbon does not have an outermost shell that's full, right? Because we can fit 8 electrons in the second shell, it's actually missing 4 electrons from being full. So there's a couple of things that I want you to know. When we're talking about the outermost shell, whether that's the first one, right? Because with hydrogen and helium, we have only one orbital shell that's surrounding the nucleus. Or it's the second one, like we see with carbon, or the third one, like we see with argon. That outermost shell is known as the valence shell, okay? So that's a term that you're gonna be seeing, and you're definitely gonna want to know what it means. The outermost shell is the valence shell. So this is our valence shell of carbon, this is our valence shell of argon. What we see, and the reason that this is so important, is all atoms want to have a full outermost shell. And the reason for that is they are most stable with a full outermost shell. So argon is actually a very stable atom. It does not react with anything because its shell is already full, and so it doesn't want to. It's already as stable as it can possibly be. Right here with carbon, we are missing 4 electrons that are needed to be able to fill up that valence shell. And so what we see with these atoms that don't have a full valence shell is they are going to be looking to react with other atoms to fill up that valence shell. And that's what we're going to get into in our next video, is talking about how these atoms actually go about filling up their valence shell by interacting with other atoms.